All right, we're in the final stretch here. We've been working on homework 10, section 5, number 6. And this has 3 carts all lined up, one of which had a velocity which collides with the next one, which collides with the next one. And this is going to be on the third part, verifying or confirming that kinetic energy of this system is conserved. We've found the final velocity of each cart. We've found and proved that the momentum of the system is in fact conserved. Now we're going to do the same thing with kinetic energy, and we'll call it a wrap. Okay? So you may need to refer back to your final velocity. Well, you know what? Tell you what. Let's write them out right now. I made the mistake of doing that, not doing that in the last video. For cart 1, the initial velocity was what we called VO. The final velocity, that is after colliding with cart 2, came out to 0.33 VO. And I can see right now that's going to be not enough room. V initial 1 is that. V final of 1, we said, came out to be a 0.33 times VO. That is after it collided with cart 2. Cart 2's initial velocity was 0, but the final velocity after the collision, we said, was 1.33 VO. That's the final velocity after collision 1. This little Roman numeral right there. You might remember that from before. And the initial velocity of cart 2 in part 2, that is as it's going on to collide with. So this is collision 2. This is collision 1 right here. The initial velocity is really the same thing as this, okay? But the final velocity of cart 2 in part 2, we did find that. And that was 0.439 VO. Okay? And 3 right here. Let's see. The initial velocity of 3 is 0 meters per second. That's really not going to come into play. But the final velocity after 2 collides with it is going to be 1.77 VO. Okay, so we care about initial velocities and final velocities of each cart before and after the collision. Okay, so let's do this exact same way we did it before. Let's start for collision 1 to 2. And what are we confirming? What are we verifying? We're verifying that kinetic energy is conserved. So that's like saying that, or that is saying that 1/2 m1, okay, mass of 1, times initial velocity of 1 squared. Remember, that's our equation for kinetic energy. Is set equal to, should be equal to the final kinetic energy. 1/2 mass of 1, final velocity of 1 squared, plus, now that you know that after the collision both carts are moving, 1/2 mass of 2 times the final velocity of 2 squared. That's what we're saying for collision 1, 2. So let's find each one individually. Again, this is our initial right here. Right here is our final. So let's calculate each one individually and see if they match up. And they should, but we want to verify that. That's our job. So initial, I-N-I-T-I-A-L, 1/2 mass of 1 times the initial velocity of 1 squared. That's 1/2 times, what's the mass of 1? 4m times the initial velocity of 1 squared. That's VO squared. We simplify that, 1/2 of 4, that's easy. So that means our initial kinetic energy for collision 1, or collision between 1 and 2, is going to be 2m VO squared. 2mVO squared. And we just have to leave that m and the VO squared in there because we don't know what they are. Okay, but they're important to kinetic energy. Let's find the final kinetic energy now. Final is going to be 1/2 m1 v final squared plus 1/2 m2, sorry, that should be v1 final, m2 times v2 final squared. Well, let's plug in what we know about each one. 1/2 m1 again is 4m times v1 final squared. Okay, what's our v1 final? It's this right here. So that squared 0.33 VO squared plus the second part, plus 1/2 times m2. m2 is 2m times the final velocity of 2 squared. Again, now this is for collision 1. So what's the final velocity of cart 2 in collision 1? 1.33 VO. 1.33 VO. That quantity squared. Okay, let's simplify this a little bit. So 1/2 times 4 times 0.33, so that would be 2. It simplifies to 2. 2 times 0.33. Oh, I'm sorry, I can't do that. Well, let's just, I'll show you what I got. I did the math here. It turns out to be 0.22 mass, or m, sorry, times VO squared plus 1.77 m VO squared, which comes out to be, well, again, because of rounding, it's close but not exactly on, 1.99 m VO squared. That's the final kinetic energy of this system. If we compare it to our initial, hey, check it out. It's the same. So that's good. Let's do collision 2 and 3, and that will be it for this problem. Okay? So down here for collision 2 to 3, we're saying for kinetic energy, and kinetic energy is 1/2 mv squared for any one object, 1/2 mass of 2 times the initial velocity of 2 squared equals, we have to set it equal to the total kinetic energy after the collision of collision 2 to 3, equals 1/2 m2 v final of 2, v2 final squared, plus 1/2 m3 final velocity of 3 squared. Just put those in brackets right there. So we're squaring that whole big thing. Okay, so we're going to say that this is our initial, all this is our final right here. Let's simply calculate them independently of each other, and that'll be it. let's do our initial below, and I'll do my final over here. So initial kinetic energy, 1/2 m2 times the initial velocity of 2 squared. That equals 1/2, the mass of 2 is 2m. And the initial velocity of 2, now remember, the initial velocity of 2 in the second part is the exact same thing as the final velocity of 2 in the first part. So we're going to say that's 1.33 VO squared, which simplifies to 1.77 mVO squared. Okay, so that's our initial kinetic energy before collision between carts 2 and 3. Now let's find our final. I'm going to start up here. Final is 1/2 mass of 2 times the final velocity of 2 squared plus 1/2 mass of 3 times the final velocity of 3 squared. Sorry, equals. All right. 1/2 mass of 2, that's 2m. What's the final velocity of 2 that is in collision 2? That's this right here. This is what the final velocity of 2 is after it collides with 3. 0.439 VO. Oops. 0.439 VO. That value squared. Plus 1/2 times, what's the mass of 3? It's simply m. Times the final velocity of 3. We said that is this right here. 1.77 VO. That value squared. All right, here's the big drum roll. Let's calculate all these out. 1/2 and 2, that kind of goes away. So it should be 0.193 mVO squared plus this simplifies to 1.57 mVO squared. We add them together. .76 mVO squared. Again, rounding makes it slightly smaller, but aside from that, they're essentially the same. So hooray, we have kinetic energy being conserved in this problem as well. So same. So that's it. We just wanted to confirm the fact that the kinetic energy was the same before and after each collision, and we've done just that. So there you go. You've done pretty much the hardest problem in this whole section, dealing with elastic collisions. And I hope it gives you just a better grasp of how to solve these. Remember, like I said in class, when batters in baseball, when they're in the batting box, they always swing bats with heavier weights on them than they need when they're in the batting box. So if you're able to do this problem, I think you should be quite fine for the test when it comes up. There you go. Let me know if you have any questions, and I'll see you in class. Take care.